and welcome to everyone who's joining us watching the recording. Let's do this. So which sections were you guys working on today? You guys were finishing up with chapter 2, right? So you did 2.6. Did you guys do 2.7? Did you guys do 2.8? Okay. All right. Okie dokies. So let's kind of get this shindig started. Do you guys have any questions about what's all going on here? Yes, no, maybe so. I, for one, at least, struggled a lot with implicit differentiation when I was first learning this. I still kind of do struggle with it. It's like not my strongest point. So I was planning on just starting off there and working through a few problems. And of course, having you guys calling me out on any mistakes that I make, because I don't know if you remember last week, but I was making a mistake probably every minute. And this is just a lot of algebra. But that was my plan, starting off with the implicit differentiation and seeing where this goes. So let's do that. How are you guys feeling with this stuff? Like on a scale of like 1 being like you cannot possibly even fathom doing it, and 10 being like you could do it in your sleep, how do you guys feel about 2.6, which is the implicit differentiation? That, like, I do have the right edition of the book, right? I'm like very concerned mildly that I have the wrong edition. You guys did do implicit differentiation this week. I think. Okay. Oh, okay. Because I have 2 copies of the book, and one is different than the other, I think, and I prefer being in the right section when I prep for these things. So we're going to start on page 166, which is the beginning of the practice problems for 2.6. And we're going to start with number 7. Okay. So the problem number 7 looks like this. X to the 4th plus x squared y squared plus y cubed equals 5. And so it's asking us to find dy dx. And we're going to be finding it in terms of both x and y. So first things first is I'm going to take the derivative with respect to x. But after I do that, I'm going to kind of rewrite this in a way that makes more sense to me using the sum rule. And again, tell me if I'm like going too slow, but this is just something I struggled with. So I'm kind of doing it at the pace that I first learned it, which was slow. So I split it up into these different pieces. And then at the end of all that, it's going to equal 0 because 5 is a constant, so we don't really need to worry about that. Okay, so this we did last week or the week before, something like that. What is the derivative of this part in the blue here? You guys can hop on audio if you want, or you can just use the chat box. Yep. All right, so that's done. Now, what are we going to do about this stuff in the green right here? Yes, we're going to use the product rule. So this is going to be plus, we're going to take the derivative of that first one, so it's going to be 2xy squared. So I took the derivative of this, multiplied by this. Now, what is my second piece of the product rule? going to be x squared times the derivative of y squared with respect to x is going to be 2y prime, or 2y dy dx. And then finally, what is the derivative of this last piece right here? Any thoughts? Yes, indeed. That's going to be 3y squared dy dx, or in this case, I'm just going to write y prime because I'm being lazy. And in this moment, I don't really need dy dx per se. So now I've got this. What's my next step? Yes, I am going to want to factor out that y prime, and so to do that, I'm going to need to do a little bit of rearranging. So I'm going to subtract 4x cubed and subtract 2xy squared from this side. So I'm going to end up with 2x squared y prime plus 3y squared y prime is equal to negative 4x cubed plus 2x, minus 2xy squared. So I just subtracted both of these from both sides. And I am just going to do this like this. I'm going to say that this is y prime times this, and I'm going to erase y prime from here. So I factored out y prime, right? And so to get my final answer, I'm just going to divide both sides by the stuff that's in brackets here, and I'm going to end up with y prime is equal to, or we'll call it dy dx is equal to negative 4x cubed minus 2xy squared over 2x squared y plus 3y squared. And you can do some factoring, like you can pull an x out of here and a y out of here, but there's nothing really you can do to like make this simpler on the whole. So if you do want to play around with the algebra, you can, but you don't have to. This would be a perfectly reasonable answer. Okay, do we have any questions about how that happens? I'm going to take your silence as a no. And we are going to do another one. Okie dokies. So we're still on page 166 right now. We are now going to do problem 11. And so that is going to be y cos x is equal to x squared plus y squared. All right, first step. What do I do? Well, I'm going to obviously take a derivative of this whole shenanigan. So I'm going to end up with the derivative of this is equal to okay. So let's do this stuff on this side of the equation first because it's probably a little easier. This first one is going to be 2x plus to y prime. Okay, so we've done that one. Now, what are we going to do about this stuff in the pink? Is it chain rule? Yep, it's going to be product rule because we're considering this to be a function and this to be a function. So we're just multiplying one function by another function. Cos x is just one function. So that means we're going to have y times the derivative of cosine of x. What is the derivative of cos x? Negative sin x. Plus, sorry, I'm kind of going at a slant here because I didn't leave myself enough room. The derivative of y with respect to x is just going to be dy dx, or in this case, I'm going to write down y prime times cos x. So I'm going to rewrite this. I've got negative y sine x plus y prime cos x is equal to 2x plus 2y prime. So, like we said earlier, my goal is just going to be to isolate. Sorry. My goal is going to be to isolate y prime. So I'm just going to do some moving around. I'm going to subtract 2y prime and from both sides. And then I'm going to add y sine x to both sides. So I'm going to end up with y prime times cos x minus 2y is equal to 2x plus y sine x. Did I make any mistakes? I don't think so. Okay. If I did, call me out. So y prime, or dy dx, is going to be equal to 2x plus y sine x over cos x minus 2y. Coolio. Awesome. Am I doing your homework problems? Or are you like doing them along with me? I do not want to do your homework problems for you. But if you're doing it along with me, then yes, that is good. Oh, awesome. Whew. All right. Let's do let's give 13 a try. So basically, the way these become more and more challenging is they add more and more pieces that you have to do in them, such as this lovely square root here. So I'm just going to immediately rewrite this and call that x plus y to the 1/2. Okay, so this stuff right here is going to be the easy part, right? We can pretty easily just look at that and say that the derivative of this is going to be 4x cubed plus 4y cubed y prime. This next chunk is going to be the nasty part. So what we need to do is chain rule, right? Because we have a function in the inside of a function. So, is everybody in agreement with me? Cool. All right, let's do it like this. If it doesn't work, then I guess we try it another way, but it looks like a chain rule piece to me. So I'm going to call f, it's going to be f of x is going to be x plus y, because y is also a function of x. And then, no, that's going to be my g. It's going to be g. So g prime is going to be x, so 1 prime. The derivative with respect to x of x is 1 plus y prime, right? So that's my g prime. Okay, then I'm going to say that f is going to be, this is going to be f of g, is going to be g to the 1/2. So f prime of g is going to be 1/2 g to the negative 1/2. Okay, that looks good to me. So I am going to put it in, meaning it is going to be 1/2. Oh, yeah. Which part? Chain rule part. You got it. Okay. So basically, I'm going to treat this just like it is like a regular old chain rule problem. Let's say that y was like a constant instead, and this was like x plus 2 to the 1/2. We would approach that in like the very same way. We'd start by saying, what's this function on the inside? And I'm calling that function g, right? And so that function g is going to be equal to x plus y. And we can do that because y is a function of x. Or at least that's what we're assuming in all of these problems. If y was a constant, then it wouldn't matter at all. But we're considering y as a function of x. So we have our g, and then we're also going to find our f, right? So f is a function of g in the chain rule. And that's the way that we know that we use the chain rule, is if they're nested functions, if you have like a function f of another function g. So that is just like a confirmation that we're doing the right thing with the chain rule here. And so if g is equal to x plus y, then f is going to be equal to x plus y to the 1/2, right? So I can go ahead and use that information to find g prime, which is going to be x, the derivative of x with respect to x, which will just be 1, and the derivative of y with respect to x, which will be dy dx, or y prime. You'll notice that I tend to hop between Leibniz notation and calling it y prime very, very frequently. So here we have f prime, and I'm still just going to call this function of g. And so f prime is going to be 1/2 g, and then 1/2 minus 1, so negative 1/2. Does that chain rule part make sense now? Awesome. Okay. So we know that our formula for the chain rule is the derivative is equal to f of g, or f prime of g times g prime, right? So we're just going to do that exact same thing. F prime of g, so that's 1/2 times x plus y to the negative 1/2 times g prime, which is going to be 1 plus y prime. So I'm going to go ahead and simplify this out a little bit. This is going to be 1 plus y prime over 2 times x plus y to the 1/2. And that looks really grody, but that's what it is. So now we get to do a bunch of algebra to sort out how to get the y primes together, right? Let's do it. Well, let's do it like this. I can simplify this into 1 over 2x plus y to the 1/2 plus y prime over, I can do this, plus 1/2 minus 4y cubed y minus. I couldn't break it up if it was in the denominator, but since it's in the numerator, I can. So I'm going to make this 4x cubed minus 1 over 2x plus y to the 1/2 is equal to y prime over 2x plus y to the 1/2 minus 4y cubed y prime. And now I can factor out y prime times 1 over 2x plus y to the 1/2 minus 4y cubed. Okay. So I'm just going to move up here now. I'm going to keep simplifying this algebraically, and again, stop me if you see an error because I make them, and I make them frequently. So let's see what we're looking at. I'm going to rewrite it. Y prime, I've got 1 over 2x plus y to the 1/2 minus 4y cubed is equal to 4x cubed minus 1 over 2x plus y to the 1/2. Okay. Just going to divide this out. So I'm going to get dy dx is equal to 4x cubed minus 1 over 2x plus y to the 1/2 over 1 over 2x plus y to the 1/2 minus 4y cubed. And I don't really like having fractions within fractions, so I'm just going to do times 2x plus y to the 1/2. I'm going to do that to both the numerator and the denominator. So what this is going to turn into is 4x cubed times 2x plus 2x plus y to the 1/2 minus 1 over 1 minus 4y cubed to x plus y. I can keep going. I can multiply these, the 2 and the 4 together. So make it so that I only have one constant in the shindig, and that one constant is going to be 2 times 4, 8. And that is that problem. Did everyone follow that whole piece? Were there any questions about how that happened? Okay. Yes. I did that to make this whole thing simpler. I had a question about why I did this. This here in the red, yes. I did it to both the numerator and the denominator. This here in the red is really gross. I don't like having fractions within fractions. So what I did is, if I have this divided by the same thing, like if I have 4 divided by 4, it's 1. And so anything divided by itself is going to be 1. So basically what I'm doing is multiplying this by 1, but my 1 happens to take the form of this being applied to both the numerator and the denominator. Does that make sense? Yes, no, maybe so. Oh, I had a 2. Sorry, I should have separated that out explicitly. What this looked like was 4x cubed times the quantity 2, like this. So this was 4y cubed times 2, right? Because I have this 2 out here. And then what I did is in another step, I just said that this is just multiplied by one another. And so I have a constant right here. And I can say that this is 2 times 4 times x cubed times this thing. So I can rearrange the order of this if I want to. These parentheses I have in the purple are not really necessary. If we envision multiplication signs throughout this whole thing, so it's 4 times x cubed times 2 times x plus y to the half. And so what I did is just say that this is 4 times 2 is 8, x cubed times x plus y to the 1/2 minus 1 over 1 minus 4 times 2 is 8 again, y cubed x plus y to the 1/2. So that happened just by me simplifying this step. That wasn't involved up here. I mean, it did happen as a result of that. But is that a little clearer? Awesome. That's what I like to hear. Okay. Let's do a couple more implicit differentiation problems. Trying to look for one that's like uniquely a mess. Ooh, 19 looks really gross. Who wants to try 19? Let's do 19. Okay. Nice. Okay. Doing something like this is very difficult to have like an analog in what we were just doing, because I guess we could try to think of how best to explain this. Instead, I'm just going to ask you guys a question. I'm going to take the derivative of both sides of this. How am I going to find these derivatives? What am I going to use to find the derivative with respect to x of y sine xy? There's no y there. Yes, I'm going to be using the chain rule. What is going to be my f function, my outer function? Yes, it's going to be sine g. So I'm just going to go ahead and find f prime right now to be cos g. Now my inner function is simply going to be xy. You can kind of think of this as analogous to when we did the whole chain rule, when we had like 4x inside. But now we have something that's a little bit more complicated. So here, G prime is going to be xy prime plus y times 1, right? Because this is a product rule that we use to find G prime. Okay. Let's do the same thing over here with cos plus xy. It's the same sort of strategy. We're going to call our f of g cos of g, and then we're going to say this is f prime or negative sine g. Here our g is going to be x plus y, so we don't need to use the product rule to find g prime. We can just say this is 1 plus y prime. We can just use the sum rule. Okay, so now that we have the components to find the derivatives of both of these, let's actually do it. This is going to be cosine of xy times x, and I'm going to put this parenthesis here because I have an addition here, and so that cosine will have to be distributed later on. So this is y prime plus y is equal to, this is going to be negative sine x plus y is times 1 plus y prime. Okay, so I'm going to have to do a lot of distributing and then bringing it back in to get my y primes first. So first I'm going to do the distribution. So I got to put cos x into both of these. So this is going to be xy prime cos xy plus y cos xy is equal to negative sine xy x plus y minus y prime sine x plus y. Okay, now I'm just going to go back and double check my signs. This should all be positive. Everything's positive there. That is making everything negative, so I have a negative and a negative. All right, seems good. Now I'm going to add y prime sine x plus y here to both sides. And I am going to subtract y cos xy from both sides, so that I can have all of my y primes in the same location. So that it's going to look like xy prime cos xy plus y prime sine x plus y is equal to negative sine x plus y, y cos xy. Okay, I'm going to go back up here. I have a room on my tablet to draw the arrow. And I'm going to factor out my y prime. So this is going to be y prime times x cos xy plus sine x plus y is equal to negative sine x plus y minus y cos xy. I'm going to divide. And my answer is going to be this. Okay. Thoughts, comments, concerns? You guys may be feeling a little bit better about implicit differentiation? Like on a scale of 1 to 10, how are you guys feeling? Oh, 9 is amazing. Wow, I don't even know if I'm at a 9. Whew. That's great. No, I'm very glad. That's awesome. We can move on. You guys are rock stars. Okay. Let me, sorry, my book isn't a PDF, which is not exactly the easiest for facilitating this type of stuff. I will say that this is my first time actually GSGing for Math 140. So I don't exactly know which exact problems are the best ones to do for GSGing. So if you guys have any suggestions about a problem that you think we should do or feedback about the problems that I've been choosing, feel free to like email me or message me in some way, shape, or form, because I am kind of just going for it right now. And some of the other classes at GSG4, they give me like lists of like, oh, these are the types of problems we want you to cover. This class did not give me that. So what types of problems in 2.7 and 2.8? These are much more application problems. So what types of problems were you struggling with? Or what types of problems did you like doing? If you think of anything, let me know. Otherwise, I was thinking about just starting off in section 2.7, so I'm on page 178 right now. I was planning on starting with questions 5 and 6. Does everybody have their books with them? Did you turn in the homework already? Okay, and then yes, we can do the homework problem. Do you want to do that before we do 5 and 6 or after? Oh, okay, let's do that now then. So we have a question from the homework about implicit differentiation. Do you want to send an image or is it on the, oh gosh, you guys are doing my math lab. You guys are doing the other one that I just completely blanked on the name. Can you send images? I assumed you can email me the image and I can open my email. Okay, that works too. All right, use implicit differentiation to find an equation of the tangent line to the curve at the given point. That's how the problem starts. And it is y sine 12x equals x cos 2y pi over 2 pi. Okay. So first things first, we are going to, I'm assuming, just use implicit differentiation here to figure out what dy dx is. Because we've got this curve and we want to find the tangent line to the curve at a specific point. Tangent line, as we've learned before, to a curve is derivative of that curve. You can find the equation of the tangent line by finding the derivative. So that's what we're going to start off with doing. All right. So for this first one, what are we going to use? How are we going to take the derivative of y sine 12x? Any suggestions? Product rule. Yep. So I'm going to start by saying this is y prime times sine 12x plus y times, and this is going to be 12 cos 12x. Is everybody cool with that? The derivative of sine 12x, you just pop that on the outside, as you remember if we talked about it last week. Otherwise, you can explicitly go through and do the chain rule to get that there. Okay. What about this chunk right here? We're going to just use the product rule again. Now we're going to say this is 1 times cos 2y, and then it's going to be plus x times 2 you know what? I'm going to just walk and do the whole chain rule shenanigan here. So I don't really think I can do this in my head, so I'm going to do this over here. If I have fg equal to cos g, f prime is going to be equal to negative sine g. That is going to mean g of x is equal to 2y, and so g prime of x is going to be equal to 2y prime, right? 2, because the constant will stay, and the derivative with respect to x of y is going to be dy dx. So, has everybody followed me up to here? Awesome. Okay. So now I'm going to put this all together to find out what the derivative of cos 2y is going to be, and that is going to be negative sine 2y times 2y prime. So I'm going to go ahead and put this in here as x times negative 2y prime sine 2y. Now I'm going to go ahead and simplify out everything. This is just y prime sine 12x plus y, or let's write this as 12y cos 12x is equal to, why did y prime receive 2, but it didn't happen in other problems? What do you mean by that? Can you explain your question a little further? Like, are you asking why, oh, okay. Good. Okay, so we were here at cos 2y plus, or rather minus 2 x y prime sine 2y. So that's where we're hanging out right now. Now we want to isolate our y prime, so we're going to rewrite this. I'm going to subtract this and add this to both sides. So this is going to be y prime sine 12x plus 2xy prime sine 2y is equal to cos 2y minus 12y cos 12x. I'm going to factor out my y prime here. And I'm going to decide to divide by that. And so dy dx is going to be cos 2y minus 12y cos 12x divided by sine 12x plus 2x sine 2y. Okay. So that is going to be the equation of the line that is tangent to the curve. Okay. I'm trying to think about how to solve a problem like this. My gut reaction is to sub in x and y, which we were given up here. So let's do that and see where we're at. I'm going to just write this in a light blue because the yellow is hard to see. So we're going to say this is cos 2y, y being pi over 4, so this is going to be the cosine of pi over 2. I'm just going to write the whole thing out so I don't lose track of anything. Okay, so this is 2 times pi over 4 minus 12 pi over 4 cosine 12 times pi over 2 over sine 12 pi over sine of 12 times pi over 2 plus 2 times pi over 2 sine 2 times pi over 4. Okay, did I sub everything in correctly? Anyone see any mistakes? Your silence is no mistakes, which is good. Means I'm getting better at algebra. Baby steps. Okay, so I'm going to bring this up here and I'm going to simplify this down a little bit further to be cos pi over 2 minus, that's going to be 3 pi cos 6 pi over sine of 6 pi plus pi sine of pi over 2. See, what's getting me here is that I'm going to end up with a number. And I don't want a number, I want an equation. Oh, it's going to just be the slope of the line? See, you guys know more than I do. Jeez. At the line? Okay. Is that what we're looking for? Yeah, it is. Jeez. That is what we're looking for. We want the equation. We have the equation. Does this not count as the equation? Maybe I should have gone through. Okay. All right. So it looks like we're doing a little more than I assumed here. Okay. So let's simplify this all out. Cosine of pi over 2. That is going to be crossing 0 at pi over 2. Yeah. So that's going to be 0 minus 3 pi. And cos of 2 pi is going to be 1. So cos of 6 pi is also going to be 1. That's going to be times 1. Divided by sine of 6 pi is going to be 0. Plus pi sine of pi over 2. The way that I'm coming up with this, by the way, is I'm kind of like thinking out, like this is what a cosine curve looks like. Not quite like that, obviously, because I'm not that great at drawing. So that's pi. So pi over 2 is going to be 1. So this is also going to be times 1. So what this is going to be is negative 3 pi over pi. So our slope is going to be negative 3. So that is the slope of the line at that point. And you guys can tell me where to go from here. Oh my goodness. The most basic form of algebra. Okay, so point slope formula. God, it's been ages since I've used this. So this is going to be y. Is it y plus the point y is equal to negative 3 times x plus the point x? Is this point slope? X minus. All right. This will just help us figure out exactly what b is. So this is y plus pi over 4. This is plus or minus. Y minus. Okay. That's a minus. That's a minus is equal to negative 3x plus 3 pi over 2, which I'm going to not write as 3 pi over 2. I'm going to say that is times 2, both of them. So that is going to be equal to 6 pi over 4. So this is going to be y is equal to negative 3x plus 6 pi over 4 plus pi over 4 is going to be 7 pi over 4. Is this kind of answer? Is everybody okay with this? Okay. I'm not seeing anyone objecting in the comments. So. Awesome. Okay. Let's do a couple from sections 7 point, or not 7, geez. This is 2.7 and 2.8. So these are kind of more applications problems, like I said earlier. And we're kind of running out of time, so we're going to move a little faster now. Let's start at problem 5 and 6 again. So these are kind of just interpreting. So let's just do 5A and 6 Let's do 5a and 6b. So 5a is showing us a velocity function, right? Oh, by the way, this is page 178. So we've got a velocity function here that looks kind of like this. Here is one. So this is t. And the question is, when is each particle speeding up and when is it slowing down? So what are we meaning by speeding up? Like what does it look like to be speeding up? Yes. So both our acceleration is going to be greater than 0. So we're going to be accelerating and our velocity is going to be greater than 0. In this case, I believe, sorry, I'm not a physics person. Physics is not my thing. But I believe that if acceleration is under 0 and velocity is under 0, it means that it's accelerating, but the particle is moving in a negative direction. So that still is like speeding up in a way. It's like one of the flaws of a question like this, like what does it truly mean to be speeding up? But I believe that if both of these cases are valid for speeding up in the way that we're going to answer this question. Yeah, I'm kind of thinking about this from a physics perspective. I did take kinematics. It was not the thing that I was best at. And so I believe because velocity is the derivative of position, right? You can have a particle that is like in a position. I'm sorry, I'm doing hand gestures here, which I realize is kind of pointless. So you can have a particle that's like in a position, and then it can move to like, if it's just like a line, it can move to a position that's up here, and if we call that initial position 0, we can say that this is a positive position and that this is a negative position because it's moving like away from its original position in like a backwards direction of the positive position. But the thing is that it's all kind of relative. So I would think through it every time and say like, okay, so my acceleration is negative, which means I am increasing my backwards speed, and my velocity is also negative, so I'm like already going backwards. So I'm just going backwards faster. And to me, that's speeding up. Again, this is like into the, yes, positive and minus specify direction with the movement. That's a better way of putting it than I kind of just babbled on about. Yeah. So we can be speeding up in the positive direction or speeding up in the minus direction. And either one is speeding up. So where are we speeding up? What is acceleration? Yes, it's going to be S double prime. That also makes it V prime, right? So where is V prime positive or negative? This is going to be positive. And then from here on, it's going to be negative. So we're speeding up from point 0 to point 1. I think Adam already said that. Yep. Speeding up from there to there. And then basically what this chunk is it's slowing down as it approaches its original position, slowing. And then it's speeding in the opposite direction. right here. We could hypothetically say that this was speeding up in the negative direction, but I don't really like that, so I'm not going to say it. Is everybody kind of okay with this problem? The struggle with these types of problems is figuring out exactly what they want from you, which is not exactly the easiest of tasks. So this is how I would answer the problem. Okay, let's try 6b. So this is basically the same problem, but it's giving us position graphs instead of velocity graphs. So let me sketch this out real quick. Okay, it looks a little something like this. This is going to be 1. This is 2, 3, and that is 4. Okay. So first things first, I would sketch just a real quick sketch of what the derivative is going to look like. I've got a 0 here at 3. So I know that that's going to be 0. That chunk, I kind of split it into chunks around my zeros. Here I have the slope is positive. And here it's going to be negative. And that's going to go out to 2, and it's kind of in this parabola shape. So I'm just going to kind of draw it as a line because the derivative of parabola is a line. So because it's this shape, I'm just going to draw a line going from x equals 2 to x equals 4. That looks like this. Then what about this chunk? I start with a very negative slope, and then it mellows out, and then it gets more negative. So I'm going to say that it's like more negative, and then, oof, sorry, this is another one that is not my strong suit, which is drawing derivatives. So this is approaching from a similar negative position. Maybe something like this. Does that seem about right? It's more negative here than it is here. All right. Now is your time to comment on my graph drawing skills. It should be up here more, right? But it looks something more like this. Because this here is approaching, it's like very shallow here. Does anyone want to comment on my graph drawing skills? I feel like that's a very large bump to have. I guess we're just going to have it like this. So I would just sketch out something to represent the velocity. Because when you're given a position, it's going to be tough to find acceleration with that. Because remember, we need both acceleration and velocity to figure out what the heck is going on here. So, all right. Where is the velocity positive? Velocity is positive from 3 to 4. And the acceleration is also positive from 3 to 4. So from x equals 3 to x equals 4, we know we are speeding up. In this case, it looks like we have a velocity that is negative, but an acceleration that is positive for most of this. And so there really is no instance where both the acceleration and the velocity can be negative. So if acceleration is not less than 0 and velocity is less than 0, by our definition, this is not an instance where we're speeding up. All right, does that kind of make sense? Like thinking about particles. Professors are a huge fan of this position. The derivative of position is velocity. The derivative of velocity is acceleration. It makes for a great example. So if you do like kinematics and that sort of stuff, you are in luck. If you don't, sorry. Okay. Let's do a couple problems from 2.8. Sorry, we're really running low on time. Oh gosh. Are we doing optimization in this problem, in this chapter? Oh. They really loaded it on you this week, and for that I am sorry. Optimization problems, like those in 2.8, I found to be very, very difficult. Mostly because it's a lot of stuff that's going on that you have to interpret. Lordy. So let's do this, I guess. I'm currently on page. What page am I on? I am on 185. Does anyone have an optimization problem they want to do? Let's try 12. I'm in the chat box. I'm not gonna read it. Okay. Oh. Okay. Particle is moving along a hyperbola xy equals 8. As it reaches the point 4, 2, the y-coordinate is decreasing at a rate of 3 centimeters per second. How fast is the x-coordinate of the point changing at that instant? Man, that's a doozy. Jeez Louise. Okay. So let's write down what we know. The y-coordinate is decreasing. So we're looking at the points 4, 2. The y-coordinate is decreasing at a rate of 3 centimeters per second. So, correct me if I'm wrong, but I'm thinking that means that dy dx is equal to -3. Does anyone have any feedback on that? Sorry, I'm looking through some of the earlier examples that don't necessarily prepare you for this type of problem. Okay, so the real trick about these problems is if any of these assumptions that you make at the beginning are incorrect, then your whole problem process is basically screwed. So what I want to know how do I phrase what I want to know? So we're wanting to know the rate of change of the x-coordinate. but it's with respect to x. Right? Yeah. Hang on for a sec. Give me just a minute. No, that's fine. Well, let's figure this one out. Let's do it. Sorry, I'm Googling it, is what I'm doing, because I'm not sure. And what Google is telling me is that what we need to consider is we're not just looking at x and y, we're also looking at time. So time is actually the what we're differentiating by. Okay, so the internet is telling me that there are two ways to solve this. One is to do implicit differentiation with respect to x. So let's do that first. So if we implicitly differentiate this with respect to x, we are going to end up with x y prime plus y, right? And we know that we're at the point 4, 2. So let's sort this out. This is x y prime is equal to negative y divided by x. So y prime is equal to negative y over x. So dy dx is equal to. And this is something, this will tell us how right I am, which is not right actually at all. Read this chunk up here. So this is going to be negative 2 over 4. So dy dx is equal to 1/2, negative 1/2. So this thing that I put up here is going to be wrong. And we know that dy dx is equal to negative 1/2. Let's find the equation of the tangent line then. Because that's another thing that we know how to do using point slope formula as we just did. So that's y minus 2 is equal to negative 1/2 x minus 4. So that's y minus 2 equals x plus 2 plus 2 plus 2. Y is equal to negative 1/2 x plus 2. Okay. So we need to figure out, yeah, okay. So something that should have clued me in about working with time and differentiating with respect to time is the fact that we're looking at something that is going at a rate of negative 3 centimeters per second. So it's not rate of change, it's rate of change particle. And so we're looking for rate of change of the particle in the x direction. If you guys have any thoughts about how to continue approaching this problem, please suggest them. Do we just check the derivative with respect to t? That seems messy. But I think that's what we've got to do. Because what this is the change in y with respect to time. So y is going to be measured in centimeters, and time is going to be measured in seconds, right? So if that's what we have, what we want is then going to be dx dt. So let's think about this. I don't even know if I need all of this. I just kind of did it because I could. We have this, and we're going to do this. So this is hey, yeah, that seems to make sense. So I think we can we sub in y and x there? I think so. Okay. So that would mean y here is going to be equal to 2 times dx dt plus x, which is going to be 4 times dy dt, which we said we have up here, which is -3 centimeters per second. So this is going to be 2 dx dt plus -12, 0, 2 dx dt is equal to 12. Dx dt is equal to 6. And this is, let's check our units here. This is centimeters per second. We're not dividing by anything, we're subtracting, so this is in centimeters per second. This is also in centimeters per second. Hey, yeah. I think that's the answer. Okay. Yeah, no problem. Sometimes it just takes a while, and that's the problem with optimization. It just takes a hot minute to sit and think through every vein. And you'll see all of the stuff in the pink and the red that I did is not really needed at all. So you can go off on a lot of tangents. But eventually, if you keep trying, you can probably figure out what's going on. And that's really what I have to say about optimization problems. Okay. Do you have any other questions? I noticed that we're steadily losing people one at a time. So if you are about ready to wrap up, then I probably am too. Awesome. All right. Well, then have a wonderful evening, and I will see you next week. Thank you for coming.